So let me remind you where we were last time. We were talking about the BCS Hamiltonian. This is the first brilliant step that BCS did. He assumed that what controls electrons at low energy, close to the Fermi surface, is this Hamiltonian that we write here. It is nothing generic, in the sense that, first of all, it has an effective attractive interaction, which is a question to itself, because electrons repel each other very strongly. And second, this interaction term is a very special type of interaction. It only takes pairs which are antipodal and scatters them to some other antipodal pair. And the generic interaction has many other processes which were just thrown away. And the idea is that this K and P, sorry, it's epsilon K and epsilon P are smaller or equal to omega d pi. So they're in some energy window. So these P and K here correspond to energies where epsilon P is this VF P minus KF. Okay, that's what we mean by epsilon P. So it's the energy relative to the Fermi energy. So now the next brilliant step that they did was the mean field they chose. So they said, let's assume that the following takes a finite expectation value. Okay, and this is a very strange order parameter because, because it is, first of all, we don't have any field. It's not like a magnetic field, for example, would couple to, it would couple to C dagger K sigma, or let's call it maybe S. Sigma S prime C K S prime, right? This would be the bilinear that, for example, a magnetic field would couple to. And the reason that real fields can couple to these kind of things is because they're gauge invariant. Right? We don't have a field which is not gauge invariant. That would be very weird, but this is what we have here. So I just want you to appreciate the fact that they did a very bold step when they assumed such an order parameter, which is non-trivial at all. They said, let's go along with this in the spirit of the Ginzburg-Landau theory, where global gauge invariance is spontaneously broken. By the way, this theory I didn't mention, but this theory can also hold to neutral particles, like cold atom gas with, for example, lithium atoms in a cold atom trap, or a helium 3. Okay, and then everything I'm going to do will have no gauge fields in it. Of course, later on we can add gauge fields, we can charge this, but everything we're doing is actually relevant also to neutral part. So the symmetry breaking that you should, so you can really think about this as like a spontaneous symmetry breaking, and the symmetry that we're breaking here is global gauge invariant. Okay, then, so how do we do this mean field? So if this is the case, we can rewrite this sum over k, c minus k down, ck up, as delta over v plus 1 over L cubed, sum over k, c minus k down, ck up, minus delta over v. Okay, this is trivial, this is obvious. But now imagine that we call this guy delta. Okay, this is some operator delta, which denotes the distance of our of these you know, what we're taking the expectation value from its assumed mean field value. So this is really the deviations from the mean field solution, this delta. Okay, and now let's assume that delta dagger delta is much smaller than delta over v, yes, squared. Okay, now when can we assume this? This basically defines when mean field is a good approximation. So it's a well-established also in the Ginzburg. I didn't mention this in the Ginzburg-Landau theory, but for example, we saw in the Ginzburg-Landau theory that we have a new minimum, and then we had a Higgs mode and a phase mode. And the Higgs mode, you can think about it as amplitude fluctuations, and you can look at the variance of the amplitude fluctuations. And when the amplitude of the fluctuations are much smaller than the mean, then it makes sense to do some sort of mean field analysis like this. Okay, it's similar to also what you've studied in crystals. I don't know if you remember your basic solid state courses, but when you develop the theory of crystals and phonons, there is this harmonic approximation. And maybe you remember that there is something called the Lindemann criterion for the melting of a crystal. Did you ever study that? Where you compute the 0-point motion of each ion, and you ask yourself, when is the 0-point motion of each ion as large as the inter-ionic distance? And that was a very crude and initial estimate for the melting point of crystals. So basically it's the same thing. So when you say, okay, I'm doing a phonon expansion of the crystal, I know that the interactions are, you know, non-linear and all this, but I'm making a harmonic approximation. In the end, what we're doing is we're writing a quadratic theory for you know, a much more complicated problem. And here we're doing exactly the same. So we have a problem which is not quadratic, and we're making it into a quadratic, and this is exactly the condition for this harmonic. So it means that the fluctuations are small. Okay, this is the idea. Now we can write, maybe we can write it here. We can write this as sum over k and sigma vf k minus kf c dagger k sigma ck sigma. And this guy, let's see what he becomes. So we can just write this this. Okay, so we have VL cubed times delta over V plus delta dagger, and then we have delta over V plus delta, right? Okay, and now this thing we can basically open it up. Okay, maybe I'll write it down here. So we can write HBCS is approximately sum over K sigma epsilon K C dagger K sigma C K sigma using this notation. And then we have minus V over L cubed. And here we make the approximation. So we have delta. Oh, by the way, let's call this delta star. The delta in principle can be complex. So this is delta squared over V squared. And then we have plus delta star. Delta over V, sorry, this is delta star over V times delta plus delta over V times delta dagger. Okay, so this is the approximation we make. Now let's open up these terms. So you see that this guy, for example, is going to have 1 over, sorry, you didn't stop me, there's a mistake here. This is V times L cubed, okay? Here there is 1 over L cubed, sum over K, right? C minus K down, C K up, okay? Minus delta over V. So when I open this thing, you see this and this is going to cancel with this, and I'm going to be left only with that, okay? Times this delta star over V. On the other hand, this guy is going to give me the same thing. So overall, I'm going to get sum over K sigma epsilon K C dagger K sigma C K sigma, and then I have a plus, okay, maybe I made some, sorry, no, minus, this is minus sum over K delta star C minus K down C K up plus delta C dagger K up C K down, okay? And then we're left with minus delta squared L cubed over V. So now the last step is I want to write this in a matrix form. So I'll write, so I want to write it like this. Sum over K, C dagger K up, C minus K down. Then I have a matrix, CK up, C dagger minus K down. And then I have here additional terms. So we'll see in a moment which terms we have. But in order to get, okay, so first of all, here we have, this is minus delta, and this is minus delta star. That's the first thing. Then here we're going to have epsilon of k. And here we're going to have minus epsilon of minus k. Right? Because in order to get this second term, we have to flip their positions and take k to minus k. And then when we flip the positions, because they, they don't commute trivially, we get, what do we get? So we get 1, right? Basically, what I'm saying is that this is 1 minus ck sigma c dagger k sigma, okay? So this 1 will contribute an epsilon of k. So, yeah, so what I get here is a sum over k, epsilon k, minus delta squared L cubed over V. Did I make a mistake here? Oh, wait a second. Wait, we need to be more careful. I messed up with the signs. Because here I have a minus. Let me see. I messed up the signs. Hold on, let me do this more carefully. Well, what? No. So this no. Yeah. Hold on. One moment. So here. This is indeed minus delta over V. So these indeed cancel like we said. But this overall has a plus sign. That's what I wanted to say. It's one thing which is important. Right? And these guys, they have a plus sign because this, when this, for example, multiplies that, it comes with a plus, but then you get a minus. So this gives us minus here and plus here. So that's a mistake. Okay? Is that clear? Questions? I think everything is fine. Okay, so now what we want to do is we want to diagonalize this Hamiltonian. So we can call this H mean field, okay? And this is our Hamiltonian, and now we want to diagonalize it. Okay, so to diagonalize this Hamiltonian, we use a very useful trick, okay, which I expect you to know, which is the fact that if you have n is a vector which is sine theta cos phi in the x direction plus sine theta sine phi in the y direction plus cos theta in the z direction, then the matrix n dot sigma, where these are the Pauli matrices, is diagonalized by first of all, okay, let's call this sigma z. Okay, sigma z meaning that this is 1 and minus 1. These are the eigenvalues, and this u here is cos theta over 2 e to the minus I phi sine theta over 2 e to the I phi sine over theta over 2 and cos, what is this, minus cos theta over 2. Okay, so how is this helpful to us? Because that Hamiltonian over there, the matrix, we can always write the matrix epsilon of k minus epsilon of minus k, delta, what do we have? Minus delta star. This matrix is actually given by VF k minus kf minus delta star minus VF of minus k minus kf. Okay, which this we can remove this and then just write k plus kf. Yeah. Oh. No, it looks like I made a mistake. Hold on. Let's see here. I think I wrote this in a confusing way, and I confused myself about this guy because in the end it's supposed to be this matrix is supposed to appear like epsilon k times sigma z plus minus delta, let's put it this way, real of delta times sigma x minus imaginary of delta times sigma y. Maybe plus, actually. But I made a mistake here. Hold on. Because this is not correct. So epsilon, okay, so let's define what we mean by epsilon k. Epsilon k originally, okay, let's understand this because this is often confusing. So epsilon of k, let's take for example something like k squared over 2m minus kf squared over 2m, for example. That could be where this is what we call mu. This is the chemical potential. And this indeed, we can write it yeah, we can define something like, say, P is K minus KF, then K is P plus KF, and then we plug this in here, we get P plus KF squared over 2m minus KF squared over 2m. And now let's assume that P is small. So we're imagining a situation where we have some parabolic dispersion like this, okay? And then we're making a linear expansion around the, so this is mu, okay? This is K, this is KF, say minus KF, this is KX or something. So the point is that this is this K over here is the total K. It's not it's not the total K. It's the magnitude of the vector K. Okay, so yeah. So this parameter, for example, it can't be negative in the sense that, you know, if I'm looking at a Fermi surface, okay, and I'm looking at 2 points, say K vector and the minus K vector, they basically have the same energy. Okay, so when I do this expansion, I want minus K and K to be the same. So basically the energy, what I'm trying to say, okay, so let me complete this thing. When I do this and I neglect small fluctuations, I basically get P, right, I get the 2 KF over 2m times P plus, you know, O of P squared. Okay, and this thing is what we call VFP, which is VFK minus KF, which is what appears over there. But the point is that when we take K to minus K, the K here, this is like K vector, if you like, and this K here shouldn't flip sign, it's just the magnitude of K. So basically what you get here is VF minus VFK minus KF. Okay? So in other words, you could view this, maybe the best way to think about it is like this. That here you have K, and here you have minus K. Okay, and in this Hamiltonian that I wrote before, this BCS Hamiltonian, when we said, you know, pairs of k and minus k, or when we took the expectation value k and minus k, we're talking about antipodal points on the Fermi surface. But they're the same energy. Okay, so it's not, if I would take this k to be minus k, I would get suddenly a huge energy compared to the Fermi energy. Okay, so that's not the point. So now you see what I mean. So this thing then becomes Vf k minus kf times sigma z, okay, which we can call epsilon k times these things. Okay, and now what we see is that phi is equal to minus the argument of delta cos theta is equal to epsilon k divided by the sorry, let me one more step. Now I can take out epsilon. Let's write it like this. I can take out epsilon k squared plus delta squared, and then I get inside the brackets I get cos theta times sigma z plus sine theta times cos phi sigma x plus sine phi sigma y as written above. Okay, like this. Okay, and under the assumption that cos theta is equal to epsilon k divided by square root of epsilon k squared plus delta squared, sine theta is equal to minus delta divided by epsilon k squared plus delta squared, and arg of delta is equal to minus phi. And it's useful to make a denote E of k as the square root of epsilon k squared plus delta squared. Now, what does this imply? It implies that we can use this formula to diagonalize the Hamiltonian, because we can basically write that H mean field is equal to a sum over k ek alpha dagger k alpha k plus beta dagger k beta k plus sum over k epsilon k plus delta squared over times L cubed divided by V. Oh, no, sorry. This is also a mistake. Let's do this. Divided by sum over k epsilon k minus ek minus plus delta squared L cubed over V. I'll explain to you where this ek comes from in a moment. This thing is what we call the ground state energy, and I'll explain that also in a moment. But before that, let me explain to you what these alphas are. Alpha K, beta dagger K. So basically what we do is, okay, look at this equation. Okay, so we take this equation, okay, and we plug in here, we put in here, we put a U dagger, and here we plug U dagger. Okay, then the matrix in the center is going to get U dagger and U, which will exactly diagonalize it. Okay, and these guys, so what we're going to get, so let me write it above, we're going to get a CK up, dagger, C minus K down, then this will be multiplied by U, then we're going to get EK minus EK, okay, U dagger times CK up, C dagger minus K down, okay, and this guy here is what we're going to call a alpha K, beta dagger K, okay, and this guy is what we're going to call alpha K, sorry, the other way around, this is dagger, beta dagger, okay, so and now, and this is 0, 0, okay, so this is, now if you flip the betas, you're going to get a minus sign, but then you're going to get an additional minus EK term here because you flipped them. So this is what you see here. Now the only thing is left is to write down what these U's are, or what the transformation is. So I'm just taking this, what's written here. So alpha K, you see? Alpha K, beta dagger K is U dagger. This is basically U dagger times CK up, C dagger minus K down, which in our case is cos theta over 2 CK up plus e to the minus I phi sine theta over 2 C dagger minus K down, e to the I phi sine theta over 2 CK up minus cos theta over 2 C dagger minus K down. And similarly, the inverse transformation, C dagger minus K down, is equal to U times alpha K beta dagger K, which will also be useful for us. It's going to be cos theta over 2 alpha K plus e to the minus I phi sine theta over 2 beta dagger K, e to the I phi sine theta over 2 alpha K minus cos theta over 2 beta dagger K. Okay, and also we need to write what are these. So now I'm going to erase all this, and let me write what explicitly what is this cos theta over 2. Cos theta over 2 is equal to it's equal to the square root. It's 1 over square root of 2 square root of 1 plus cos theta, which is 1 over square root of 2 square root of 1 plus epsilon k divided by ek. and sine theta over 2 is equal to 1 over square root of 2 square root of 1 minus cos theta, which is equal to 1 over square root of 2 square root of 1 minus epsilon k minus k. Okay, so this is just this is generally useful to diagonalize 2 by 2 Hamiltonians, which is about 30% of what you do in physics. So you should know this. This is a good example, but this is kind of generic. This transformation is known as the Bogolyubov transformation. Okay, and we've already encountered a Bogolyubov transformation when we did the superfluid problem. We did mean field. It was very similar in spirit. We took small fluctuations, neglected fluctuation squared, and so on and so forth. But if you remember, then we used cosh and sinh functions, and the reason was because we needed a transformation which is canonical in the sense that it conserves the commutation relations. For bosons, you need to use cos hyperbolic and sine hyperbolic functions. For when you do a Bogolyubov transformation, for fermions, you can use cos and sine, which is more convenient because the transformation, the canonical transformation, is also unitary. Okay, just the rotation. Okay, so we diagonalize the Hamiltonian. That's nice. Let me say something about the dispersion. So the point is, we can, if we look at this Hamiltonian, okay, and we draw, basically we draw epsilon of k versus k, then we're going to have something like this, okay, where this is basically kf, okay. This is, this is like, I don't know, k squared over 2m minus mu, something like that. Then we can draw also a minus epsilon of minus k would basically look something like this. And that's what sits here. These are the holes. So this would be like down particle, and this would be the up particle. And what we see that superconductivity is essentially, you can view it as a hybridization between two bands. Okay? Now it's engineered in a way that we have this kind of symmetry because we took the same band and just flipped it. Inherently it has what we call a particle-hole symmetry, which is special for these cases. So once we add delta, what this delta does, it creates an avoided crossing between this band. So instead of having this crossing here, we're going to have some hybridization here and here. Okay? And here we have delta, and here we have delta, where this lower branch is now what we would call beta dagger, and this upper branch is what we would call alpha. Okay? Once we switched and or took beta dagger the way we decided to, then actually you can see that it's like flipping this dispersion, and then all the excitations are positive in energy. Because for fermionic systems, I don't know if you've ever thought about it, fermionic systems are such that everything below 0 is occupied, everything above 0 is not occupied at 0 temperature. So if the dispersion looks like this, it means that everything here is occupied. And then we have a lot of Bogolyubov excitations that are occupied and a bunch of Bogolyubov excitations that are not occupied. This is a useful way to interpret it if we want to think about it like a semiconductor kind of model. So you have everything occupied, you have a band gap, which is delta. Okay? By the way, this is 2 delta. This is not delta. This is 2 delta. You have a band gap of 2 delta, and which is exactly what you need. It's the energy you need to break the Cooper pair. But the there is enough, but I chose to write it the other way around. By the way, the only thing you really need to do in order to do this semiconductor description is just call this beta, and this beta, and that's it. You're done. But then you'll have a minus sign, the problem with this interpretation is that whatever you're left here is not the ground state energy anymore, because you need to occupy all these states. Now, why did I choose to write it like this? Because then you see that at zero temperature we have no excitations, and each excitation can be interpreted as breaking a Cooper pair, and then the ground state energy is what is written here. That's basically the energy with no Bogoliubov excitation. And what these excitations describe, they describe basically fermionic excitation. Every time we break a Cooper pair, we create two fermions. And these fermions have energy. And this energy is denoted by these excitations. And that's something that Ginzburg-Landau theory does not capture. There are no fermions in Ginzburg-Landau theory. These excitations don't exist in Ginzburg-Landau theory. In fact, the Ginzburg-Landau theory that we wrote assumes no Bogoliubov excitations. They don't exist. Okay? So once, so this is what BCS theory gives us that Ginzburg-Landau theory doesn't give us. It gives us the fermionic side of the picture. Okay? Now, often, in many cases, for example, if you would take a superfluid, which is not a superconductor, like helium-3. You start from fermions, you cool it down, it turns out that below, I don't know, 100 milli-K or whatever, helium-3 becomes a superfluid. So first they pair, then they create, then the low energy excitations would be the Goldstone mode of this superfluid. And it would be much lower in energy than this gap. And then it's fine. Then the Ginzburg-Landau theory, basically, if you really focus on the low energy physics, it's just that. But in a superconductor, once you charge them, then this Goldstone mode gets Higgsed away, and it becomes actually the plasma frequency. So suddenly it becomes huge in energy. And then the lowest energy excitations can sometimes be the fermions. And this is what happens in BCS theory. So in BCS theory, suddenly it's much more important. If you want to capture the low energy asymptotic behavior, you want to focus on what you expect to see, like the lowest energy excitations, which you can capture, then suddenly the fermionic excitations become important. And this is why BCS theory also was so important, because all this wasn't captured by Ginzburg-Landau theory. So for example, if we will, at the end of this lecture, we will see the specific heat, for example. So people measured specific heat of superconductors, and Ginzburg-Landau theory was anything near that. Couldn't explain this phenomenon. Okay. So all this is nice and good, but there is a elephant in the room. Okay, and the elephant is the fact that we don't know what delta is. Okay, we just assumed some delta. But in order to complete the story, we need to determine delta self-consistently. So how do we do that? This is the basics of mean field theory. What we do is we write delta is equal, we defined it. So it's basically 1 over L cubed, sum over K, right? The expectation value times V. Where is V here? C minus K down, CK up. Okay? And here it's very important to be exact. So I'm writing exactly what we wrote before. Every time someone leaves the room, it's like 2/3 of the class just got up and left. It's a dramatic effect. Okay, so now, how do we solve this guy? Well, I remind you that they do not diagonalize the Hamiltonian. The Hamiltonian that is diagonal is this. You see, the beauty of this Hamiltonian is that these guys will be occupied according to Fermi-Dirac distribution because they're fermionic excitations. That's actually the meaning of quasi-particles. The fact that we wrote some effective theory that has these kind of excitations, basically like a quadratic Hamiltonian, and at low energy, these are the excitations that you would start populating as if they're like free fermions. They're not really free fermions. They emerged from some interacting Hamiltonian as a mean field solution. They are, have some inherent interaction effect in them, which is this gap and so on and so forth. But on top of this interacting ground state, there is, bubbling are these excitations, and we take advantage of that. So now we write, you see, instead of this C minus K down, we will take this guy, dagger, okay? And instead of this CK up, we will take this guy. Now, I'm also going to assume that phi is equal to 0. Why can I assume that phi is equal to 0? Assuming that phi is equal to 0 is like assuming that this delta is real. Now, I can always do that because I have... Sorry, this is a... I remind you that if this is a superfluid, this is a spontaneous symmetry ring. If this is a real superconductor, then I can just do a gauge transformation. In any case, I can get rid of this, and that's just going to be convenient because then I don't need to track these guys. Anyways, I get V over L cubed expectation value of this guy daggered. So I have sine theta over 2 alpha dagger of k minus cos theta over 2 beta k, and this whole thing is multiplied by cos theta over 2 alpha k plus sine theta over 2 beta dagger k. Okay, now because this Hamiltonian, the advantage of doing this in the diagonal basis is that now there are no correlations between alpha and beta. So this expectation value will give me the Fermi-Dirac distribution, and this will give me 1 minus the Fermi-Dirac distribution of the betas. Okay, so I get what do I get? I get V over L cubed. Oh, this is V over L cubed. V over L cubed sum over K. Blah, 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 blah. So I get sum over K. Sine theta over 2 cos theta over 2, and then I get n Fermi-Dirac of Ek. This is from these guys, and then I get plus 1 minus n Fermi-Dirac of Ek coming from these guys. Okay? And then I want to point out that this guy, according to everything we wrote on this board, okay, is minus sine of theta, right? Because I remind you that sine theta had this minus here. Okay. Because of this delta. Because the way we define these guys, you multiply them. Okay. And this guy is, what is this? This is the hyperbolic tangent of EK over 2 times t, as Joseph can take. Hi. Okay. And so overall we get that this is equal to V over L cubed, sum over K, let's write here delta over EK tangent hyperbolic of EK over 2t. So we get, this is what we call the gap equation. Okay, and now we need to solve this gap equation in order to determine what delta is. And notice that this gap equation is not a linear equation. Okay, but let's solve it, and then maybe we can go on a break. So I first want to mention that 1 over L cubed sum over K, I will write this as 1 over minus KD to KD dk times KF squared, which means that I'm going to do a small integral over the relevant range. So I remind you, all the sums over K and so on and so forth are just in this ring. Okay, so I remember we have, like, this is KF, and we have a ring, and this is like, you know, this is plus, the width of this thing is like 2kd. Okay, and maybe I shouldn't call this K, let's call it a Q, I don't know. Q is like, you know, the distance from the Fermi energy. Okay, so this is some small, yeah. So then I obtain the equation V, and then I have K F squared. Sorry, and this is divided by 2 pi. Sorry, this is divided by 2 pi squared, right, in 3D. Let's assume that we're doing 3D for now. Is this clear why it's 2 pi squared? Or any questions? It was, so, okay, let me do this a little bit slower. So this thing is d3k over 2 pi cubed, but now we're assuming that everything is spherically symmetric, because in the integral you see everything depends only on the magnitude of k. This is k. So we can make an expansion around the Fermi surface. So we have basically kf squared, okay, divided by, now imagine that we did an integral over phi, the angle phi of k from 0 to 2 pi, so we get 2 pi. we did an integral over cos theta from -1 to 1, so we get 2. So we get 2 pi squared left. That's what we get. And then we have an integral from kf minus kd to kf plus kd dk. That's what we have left. That's it. Okay? And this thing, I will call this q. So q will be relative to this thing. So I have here 2 pi squared, the integral from minus kd to kd dq. And then I have delta divided by the square root of vfq squared plus so now delta is real, so just let's call it delta squared times tangent hyperbolic of square root of vfq squared plus delta squared divided by 2t. T is the temperature. Yeah, I want you to notice, so a few things to notice. First of all, we can of course cancel this here and here, and then just make this into 1. The second thing I want to point out is that if we take delta to 0, okay, maybe let's leave that for later. Second thing, let's define VFQ as equal to epsilon. Okay? Then, if we define this, then we get the equation is equal to lambda, the integral from minus omega dpi to omega dpi. Oh, wait a second. Probably I made a mistake with the 1/2 here. Hold on one moment. This is important. This is a factor of 2. Factor of 2 is always very important. I made some sort of mistake here with the factor of 2. 1 second. Where did I define lambda? Why didn't I define lambda? Lambda. Oh. Okay, so let's call this lambda over 2. I'll explain in a moment. And here we have d epsilon, 1 divided by epsilon squared plus delta squared, tangent hyperbolic of square root of epsilon squared plus delta squared divided by 2t. Okay, this is a nice compact form where lambda is equal to kf squared over pi squared Vf, which is the density of states times V. Density of states. Okay, this is this lambda, and this is it has no dimensions. It's a dimensionless parameter, Okay? And this is, by the way, the density of states. So I remind you that the density of states, it tells us how many states are in a small window delta epsilon. Okay? And V has units of energy, 1 over density of states. Energy times volume, basically. So the product of these two, okay, tells us something about the ability of the interaction to mix states. Okay? When V is much smaller than the density of states, it means that if you take a small piece of the system, a small volume, then you're going to get some quantization of states there, and the effective interaction strength at that volume is going to be smaller than the level space. So it can't mix with mixed state. It means that the interaction is probably not going to do anything dramatic. On the other hand, if V is much larger than the density of states, lambda is larger than 1, it means that it mixes, it will have a dramatic effect. So we know that in order to have some interaction effect, lambda needs to be of order 1. Okay? So when we do perturbation theory, for example, we can only say something asymptotic in the limit of small lambda. Then we can try and make some expansion of all sorts of results in terms of small lambda. Okay, so we could imagine trying to do some sort of power series in lambda. Okay. Now let's continue. So this, let me continue it here. Oh, hold on, let me write here above something. Write somewhere that the H mean field is sum over K alpha EK alpha dagger K alpha K plus beta dagger K beta K plus E ground state, and this E ground state is equal to sum over K epsilon K minus EK plus delta squared L cubed divided by V. So this is just, let's keep that. Now let's solve this integral, and let's start from 0 temperature. So in the limit t equal to 0, so this tangent hyperbolic just becomes 1. So we just need to do this integral, and then it's very easy because this is the integral of this is a hyperbolic sine function. So we get the inverse hyperbolic sine function. So we get 1 over first of all, one thing I want to point out is that let's erase this, put lambda here and put 0. We can always do that because everything here is symmetric, plus and minus epsilon. And then we get 1 over lambda. Okay, so we can also erase lambda here and write 1 over lambda is equal to that, which is nice. Okay, so we get 1 over lambda is equal to a inverse sine hyperbolic function of omega debye over delta, and that implies that omega debye over delta is equal to a sine hyperbolic of 1 over lambda Or in other words, delta is equal to omega dpi divided by sine hyperbolic of 1 over lambda. But we didn't discuss this, but it turns out that this theory is only valid when lambda is small, for reasons that you can't understand right now. I didn't explain it. So in that limit, we can say that this is omega dpi e to the minus 1 over lambda. Right? Because the sine has an exponent and an exponent of minus this. And if we take lambda to be small, then it's going to be dominated by that. Okay, so this is a very well-known result. There's a 2 here. Why 2? There's 2 because it's 1 over sine. Right? Sine hyperbolic of 1 over lambda is e to the 1 over lambda minus e to the minus 1 over lambda over 2. This is this 2. So this is a well-known result of BCS theory. This is the size of the gap. And I want you to notice something very important. Do you know how you call this? What is this form? If I would want to think about this in the space of lambda. So let's say I think about this function as a function in the space of lambda. What does this function have at lambda equal to 0? How is this?
It's a maximum. It's going to 0, right?
Well, it's going to 0, but it's a singularity.
Right.
It has a singularity, right? How do you call this singularity? Do you know?
Essential singularity.
It's an essential singularity. Exactly. And what does an essential singularity mean? What do we mean when we say essential singularity?
That we cannot expand around the current.
So exactly. So you can't write this as a power series. You cannot write an asymptotic power series. Okay. Around this, and this tells us that this is a non-perturbative result. We couldn't have obtained this. We couldn't have imagined obtaining this from some sort of perturbation expansion in lambda. Okay? Because as you make lambda smaller and smaller, basically higher and higher terms become more and more important. And this is something that you will find common in mean field theory. Mean field theory is non-perturbative. Okay, it gives us non-perturbative results, but still this result is actually only accurate at small lambda. And we could never imagine of obtaining this result from perturbation theory. Okay, what we have. Okay, so we arrived at this result. Now let's also use this to compute TC. Okay, so how do we compute TC? So this was a... so regarding what we talked about before, Joseph, all your integrals should in the end come up somehow to integrals like this, which you can do at temperature 0. That's just inverse the inverse sine hyperbolic sine function. Okay, so to obtain TC, we assume delta equal to 0. So basically what this equation is telling us, this is a self-consistency equation. And if you remember, we started with delta here and delta there. And as we teach any, a high school student, or even before that, if you eliminate something from the function, you need to remember that 0 is also a solution. Okay, so we can't divide by 0. Okay? So So delta equal to 0 is always a solution of this equation. But what we're searching for is not just delta equal to 0 solution, but the first non-trivial solution. And the way you can imagine doing this is that we're looking for the other branch, which is this branch. So once we eliminate the delta, we want to know when this branch develops a solution, but we want to set delta here and delta here to 0. So basically, we can obtain Tc by solving the equation 1 over lambda integral, 1 is equal to 1 over, 1 over lambda is equal to the integral from 0 to omega dpi, the epsilon over epsilon, tangent hyperbolic of epsilon over 2Tc. And here you can see something important, which I should have already mentioned before, is that there's always a solution. There's always a solution in the sense that if you have fermions and they have attractive interaction, they will always become superconducting. Okay? And you can see this from here, because what this function does is that when epsilon is much smaller than Tc, okay, then this is a linear, right? If I draw the hyperbolic tangent, it looks like this. Okay. So then this epsilon and this epsilon cancel, and you get a finite result. So basically this tangent hyperbolic. Now, if epsilon is much larger than Tc, then it diverges. Okay. Then it goes like 1 over epsilon. And what that tells you is that this Tc here basically cuts off the integral. So the smaller, now the range here, this here, is basically of order 2Tc. Okay? So once, minus. So once we take Tc to be smaller and smaller and smaller, the cutoff for this divergence, this 1 over epsilon, this logarithmic divergence, becomes smaller and smaller and smaller. So it means that there, no matter how tiny lambda is, we can always find the Tc such that this integral would be large enough and satisfy the equation. And this is a very important result because it's not very easy to destabilize Fermi liquid. I'm not teaching Fermi liquid theory, but in Fermi liquid theory, one can show or argue for the stability of the Fermi surface with interactions. This was basically one of Landau's huge contributions was to notice that if you take into account the interaction effects on top of a Fermi liquid, you find that as you lower and lower the energy around the Fermi surface, then the phase space for scattering becomes more and more limited. And as a result, the quasi-particles have a lifetime which becomes longer and longer and longer until you get sharp quasi-particle excitations at the Fermi surface, which was an argument for the stability of the Fermi surface. But Landau did not think about this kind of processes, these scattering processes that go, that scatter antipodal states across the Fermi surface, and these actually lead to an instability. They destroy the Fermi liquid. The Fermi liquid is unstable to these kind of processes, and basically it means that it's unstable to any attractive interaction. Without an attractive interaction, it will also have attraction in this channel. By the way, that's another thing you should notice, that this equation, it doesn't have a solution if lambda is negative. Lambda is negative, it means a repulsive interaction. So that's another thing that it might be good to point out, and this is something that, for example, Amir is studying right now, is that if you take a generic screen interaction, you'll find that there's always some high angular momentum channel. Okay, so here we took delta to be a constant, which is like the S wave. We took singlet, S wave, superconductivity. By the way, the interaction we took was singlet-singlet interaction. But the generic interaction will contain also triplet-triplet and so on and so forth, and you can have higher angular momentum channels, and we neglected all this. But if you allow all these things to happen, you'll find that for a generic screened interaction, there is always some attractive channel at high angular momentum. And then it implies that at low enough temperature, any metal becomes superconducting because of this. So what it implies is that as long as you have time reversal symmetry and you're not thinking about quantum Hall states and all sorts of stuff like that, at least this is common knowledge, which is what the Tamir is trying to challenge right now, is that the superconducting ground state is inevitable. Any metal, at least from the conceptual point of view, is a superconductor at zero temperature. Now, what you see from this expression is that Tc, if lambda is tiny, Tc might need to be also very, very, very tiny in order to obtain it. But it's always there. So it means that these kind of processes, they always destabilize the Fermi surface. And if I already talked about the stability of a Fermi surface, there is another way to destabilize the Fermi surface. And that is if you couple the fermions on the Fermi surface to a soft boson, in the sense that a Goldstone, for example, if you take a Goldstone boson and you couple it to the Fermi surface in a way that can alter the Fermi surface, this is what happens near quantum critical points, for example. Goldstone-like mode. Don't want to get too much into the details. Then this is another way to destabilize the Fermi surface. But it's very hard to destabilize Fermi surfaces. And this is one of the ways. And then this equation, okay, so we can do this equation and we can solve this equation kind of in a rough way. So maybe a rough way would be to say that the integral from 0 to omega d by the epsilon over epsilon of tan hyperbolic of epsilon over 2tc is more or less like an integral from 0 to 2tc, which is the small epsilon regime, the epsilon plus the integral from 2tc to omega d by the epsilon over epsilon, which is basically like, it's basically like approximating this function like a line, and making a sharp transition to a constant, which is 1. And then this thing gives us a 2tc plus ln of omega d by over 2tc. And and then you can see that you get, so we can move this to the other side. We get that ln of omega d by over 2tc is equal to 1 over lambda minus 2tc. And then we invert this, and we get that tc is equal to omega d by over 2 e to the minus 1 over lambda plus 2tc. Sorry, this is no. This is this is going to be a bit more tough to calculate. Then we need to do wait a second. Then it's a bit, how would I do this? One moment. Oh, wait a second. No. Something here is problematic. Oh, no. I can't, wait. I'm doing shtuyot. and you're not stopping me. This guy here is sorry, this is the epsilon over 2tc. The epsilon over 2tc, right? Because when I do a linear expansion, this has to have no dimensions. Sorry, so this gives a 1 over lambda is equal to 1 plus ln of omega dpi over 2tc, which gives us that tc is equal to omega dpi over 2 times e to the minus 1 over lambda. Okay, or maybe we can write here plus 1. Okay, this is like a rough way of doing this integral. But you can do better than that. And the result that we get from doing some more sophisticated integration is this result. Where gamma is the Euler constant, 0.577. Okay? So this is the result for TC. And this leads to one of the famous predictions of BCS theory. This leads to one of the famous predictions of BCS theory, the TC over delta, right, is equal to e to the gamma. This is pi, by the way. This is not t. E to the gamma over pi, which is a 1 over 1.764. Or in other words, delta over TC is equal to 1.764. Okay? And this is a well-known prediction of BCS theory. And in my notes, there is a comparison between a bunch of superconductor like aluminum, tin, niobium, all sitting on the line. And but if you look at some unconventional superconductors, like so you can take, first of all, cold atom gases that are close to the Feshbach resonance, where the coupling is very strong, or you can look at what you call them, high TC superconductors, organic superconductors, and so on and so forth, and you'll see that they deviate from this relationship, and typically it's above, in the sense that what happens in a strongly correlated superconductor is that delta is greater than 1.764. So for strongly correlated superconductor, this is what we have. And the idea is that you can imagine that the interactions are very strong, so they lead to a very strong gap. But what destroys superconductivity and gives us TC is not the closing of the gap, but some other fluctuations which are not taken into account. So for example, like phase fluctuations, for example, can lead to a BKT type transition, and that's just an example. Okay, but the stiffness, say the stiffness of the superconductor is much weaker, and then we get that delta is actually larger than this relationship. Okay, now let's talk about the BCS wave function. Any questions about this? So we can derive the BCS wave function by demanding that it has no Bogoliubov quasiparticles, that alpha of k equals beta of k is equal to 0. So this is basically our ground state. Our ground state is a state that if we act on it with the destruction operators of Bogoliubov, then it gives us 0. And then I remind you what I erased already. Let's see. Is that alpha of k, the operator, is cos theta over 2 ck up plus sine theta over 2 c dagger minus k down. Okay? Yes. Okay? So, let's call this a ground state. Okay? So, what we find, therefore, is that the condition is that cos theta over 2 ck up ground state is equal to minus sine theta over 2 c dagger k minus k down ground state. Okay, so let's work with that. So if we look at this structure, okay, we can make an ansatz that the ground state is a coherent state of the CK ups. Okay, because we're acting with CK up and we get something. Okay, actually we can read it from here. We can say that CK up ground state is equal to minus tangents of theta over 2 C dagger k minus k down ground state, and therefore we can conclude that the ground state. Okay, so first of all, let me remind you that we had this relation. So this is reminder. So C acting on eta gives us eta eta, where the state eta is e to the minus eta C dagger acting on the total vacuum. The vacuum in our case is going to be the Fermi C state. So using this, we can just, you see, we can just plug this guy here, where instead of C dagger, we have this C dagger K up. So all we really have is just E to the tangents of theta over 2, C dagger minus K down, C dagger K up, and this is equal acting on the vacuum. Okay, and we also need some sort of, so this is the ground state. Now this is of course supposed to be relevant for every K, so we need to add here some a normalization and a product over all k. Okay, and this and tangents of theta over 2, tangents of theta over 2 is, we know it. This is basically 1 minus cos theta 1 plus cos theta square root, right? So now, the only thing we have left to verify is the normalization. So assuming this state is normalized, we can just compute the normalization by looking at ground state and demanding that this is 1, but this gives us 1 over n squared pi of k, 1 plus tangents squared theta over 2. So we can conclude that this 1 over n, each factor of 1 over n is okay. So we can conclude that n is equal to the square root of 1 plus tangent squared of theta over 2, and then so let's write it the other way around. Let's assume that the pi over k has the 1 over n here, so we have all these factors for all k. But this guy just gives us cos, right? This gives us cos theta over 2. This guy is just, what is this? This is square root of 1 plus sine squared theta over cos squared theta over 2, which is 1 over cos theta over 2. Okay, so we get that the ground state, the normalized ground state, BCS ground state, is pi over all k states cos theta over 2 minus sine theta over 2 c dagger k up, c dagger minus k down, acting on the vacuum. And this is sometimes helpful. So if you want to compute, you can do all sorts of computations just with this wave function. Sometimes it's useful. For example, you can compute expectation values in the original Hamiltonian just using this ground state. In terms of because this, you see, this allows us to go from the ground state of in terms of the Bogoliubov bonds, which were destructed by, alpha and beta, to the state that is the ground state of the original Fermi liquid, which is destroyed by the C's. So that's sometimes useful if you need it. Another important result is the ground state energy. So, what is the energy gain from the condensate? Which is something we also estimated in the Ginzburg-Landau theory. So, in the ground state at t equal to 0, we have no excitations, and therefore we just need to compute E ground state. Which is sum over K VF K minus KF minus EK plus L cubed delta squared over V. But this has, some energy. This will give us some result. But this is not what we're really interested in. We want to know the energy gain from forming the condensate. So we want to compare this to the original energy. So we also have the normal state energy, which is a sum over K, basically 2 times VF K minus KF times theta of K minus KF. KF minus K. KF minus K. Okay? So then the energy delta E is equal to E ground state minus En, and if it's beneficiary, if we gain energy from this, this should come out to be some negative number, and that tells us how much energy the system gains from forming this super state. So let's work that out. By the way, just as a comment, and this is how BCS did it in their paper, the original work, you could also do the same computation using this ground state over the original Hamiltonian. Just take the original interacting Hamiltonian, you can work through, and this appears in BCS paper, and you can do the same thing. Here we use the mean field Hamiltonian, which is easier, just have an expression for the ground state energy. Okay, so what do we have? So we have that delta E is equal to a sum over K larger than KF of VF K minus KF minus EK. But for K smaller than KF, we have minus. So we have minus sum over K larger than KF. And then we have VF K minus KF plus EK. Plus this delta L cubed, delta squared over V. Okay, so now, what do we do now? What do we do? So assuming, all these integrals, again, are computed up to omega d pi, and there's symmetry to, energies above and below omega d pi. Then what do I want to say? What do I want to say? Yeah, so I want to treat this guy, let's call it P. Okay, and I'm taking P from, minus k debye to plus k debye. So what I want to argue is that this thing is equal to 2 times what?
Doesn't that term cancel with the first one?
Which term?
That P with the first in the first song, we have the same.
Oh, sorry, this is smaller. It's a mistake. Okay, so this is the region of k larger than kf, and the region of k smaller than kf. Okay? So this thing becomes equal to 2 times the integral, the sum over k. Which one do I want to take? Hold on, let me see. Yeah, of k larger than kf. So I'm converting this guy into k larger than kf, and ek doesn't depend on k larger or smaller than kf. It's symmetric. Symmetric about that point. So we get Vf k minus kf minus ek. Okay. Plus this delta squared L cubed over V. So now we can make this integral into something. So we can write that this is equal to 2 times L cubed, the density of states, which is kf squared over pi over 2 pi squared Vf, the integral from 0 to omega debye, the epsilon of epsilon minus square root of epsilon squared plus delta squared plus delta squared L cubed over V. Okay? So what I did, so this is basically this. So here I've just used the fact that epsilon is equal to Vf k minus kf, and I made the integral over 0 to 2 pi over the angle phi, and from minus 1 to 1 of cosinus theta, and all the rest just follows like before. Okay, this is not k, this is v. Now we can just perform this integral, and what we obtain is the following result. So this is an integral one can solve. One gets L. Okay, and now let's call this guy, let's call him n of 0. This is basically the density of states per spin at the Fermi level. Yeah. Okay. So then we get L cubed, density of states, omega debye squared, 1 minus the square root of 1 plus delta squared over omega debye squared, plus L cubed, n of 0, delta squared, ln of delta divided by omega debye squared plus the square root of omega debye squared plus delta squared. So I swear to you that if you just plug this in Mathematica or something, you'll get this result. It's a straightforward integral. plus delta squared L cubed over V. And now we can just plug in delta is equal to 2 omega d by e to the minus 1 over lambda. Okay? And lambda is equal to n of 0 times v. Okay? So, and here, what you see here, we can neglect this thing is approximately delta over 2 omega d by. You see that? So that means that this gives us minus, basically this whole log just gives us minus 1 over lambda. Okay? Here, what do we have here? So here, we can expand this. Okay, so let me start from this. So here we get minus 1 over lambda. Yeah, so we get minus 1 over n of 0 v. But then the n of 0 here cancels with the n of 0 there. And then this basically cancels with that. So we're left only with this. So we get that this is equal to L cubed, but then we have omega d by. Now we can expand this, so we get omega d by squared. We get 1 minus 1 minus delta squared over 2 omega d by squared. Okay, and then this and this cancel, and we get minus L cubed. Sorry, there's n of 0 here. Forgot n of 0. N of 0. So we get n of 0 delta squared over 2. Okay, and this gives us the condensation energy. Okay, it is exactly the size of the gap delta times the density of states. It's basically the amount of states we can put in delta. That's what we gain from condensing. And this is a very important result because, for example, if we had the energy, you remember that when we computed HC1, it was a very messy calculation that I did back then. But basically, we had a vortex. And then there was a line energy, which was built out of two contributions. One was the core energy, and the other one was basically the phase winding, this logarithmic term, whatever. And the core energy is exactly this. So the core energy can be taken to be n of 0 delta squared over 2 times psi squared. That would be the core energy. This is energy per length. Because when you multiply it by L cubed, you get energy. And this is, for example, core energy of the vortex. It's the core of the vortex where we need to nullify the order parameter in order to have a vortex. Oh. I see I'm kind of out of time now. So the last thing I wanted to do is entropy and specific heat. I have 10 minutes, right?
Yeah.
Okay, so let's try and do that in 10 minutes. Another important prediction of BCS theory is the specific heat. So one of the advantages of having these Bogoliubov quasi-particles is that we can treat the problem as if these Bogoliubov quasi-particles are some non-interacting particles that bubble on top of this interacting ground state. And then, for example, the change in free energy due to these excitations is just minus T sum over K ln of 1 plus e to the minus ek over T. What is this? This is the result that I remind you we got way back when we computed, when we talked about field integrals. We estimated the free energy of the free particles, free fermions. Now we have these free fermions. And by the way, this K, we also need to have this alpha beta thing. So we integrate over two types of particles. And then we can get basically S, the entropy, is dF dt with a minus sign, right? So we can compute dF dt, and this comes out to be sum over K ln of 1 plus e to the minus ek over t plus ek over t n Fermi Dirac of ek. This is just straightforward calculation. And then we can use the fact that ek over t is equal to log of 1 minus n Fermi Dirac of ek minus log of n Fermi Dirac of ek. Okay, you can just check this, and that log of 1 plus e to the minus ek over t is equal to minus log of 1 minus n Fermi Dirac of ek. And then we can rewrite this S, the entropy, as minus 2 times the sum over K. This is the sum over alpha and beta gives us this 2. So we have 2 now, because they're identical. 1 minus n Fermi Dirac of ek times ln of 1 minus n Fermi Dirac of ek plus n Fermi Dirac of ek times ln of n Fermi Dirac of ek. And this is, by the way, generic for any dispersion relation. It doesn't matter if it's superconducting to the magnet, if it's just a regular metal. This is the entropy of a free fermion system. And what it basically counts is, you see, if n Fermi Dirac is only 1 or 0, so imagine at 0 temperature n Fermi Dirac is just 1 or 0, for example, then you're not going to have any entropy at all. Because, you see, when say n Fermi Dirac is 0, then this gives 1, and 1 gives us 0 because it's log of 1. And here it's 0 times log of 0, which is also 0. So basically it just gives us 0, but only in between when we have some excitations which are partially occupied, and then we start to have entropy.
It's like saying at T0 there's no uncertainty of how the system will arrange.
Yes, exactly. Or at least it's sub-extensive. Okay, now we can compute CV, the specific heat at constant volume, which is T ds to dt, which in our case is twice the sum over K sec hyperbolic squared of ek over 2t divided by 4t squared times ek minus t ek dek over d delta over dt, fun times, and this is equal to 2 times sum over k sec ek over 2t divided by 4t squared ek squared minus t over 2 d to dt of delta squared. Okay, so this is a much more useful term, and now we can estimate this term in two different limits. One limit is where t goes to 0. So in the limit I now noticed that I forgot to mention something. So our general equation before was 1 over lambda was equal to a sum over k, or maybe let's write it like this: 0 from omega divided the epsilon of tangent hyperbolic of square root of epsilon squared plus delta squared divided by 2t divided by square root of epsilon squared plus delta squared, right?
Right.
So we solved this in two distinct limits. We got here delta of 0. This is t, this is delta of t, okay? And we obtained here tc, and here we obtained 2 omega divided by e to the minus 1 over lambda, right? This is the result we got. But in between it does something like this, okay? Which is something that Yael saw many times, okay? She's not even smiling, she's suffering that much, you see? But what you can notice is that in this regime, the dependence on temperature is very weak. So we can look at this term where we have d to dt of delta squared at small t. That basically cancels. So at t much smaller than tc, delta of t is more or less delta of 0, and it's a constant of delta. And then we obtain that cv is equal to 2 times the integral from delta to the square root of epsilon squared, omega divided squared plus delta squared, sec hyperbolic squared of epsilon over 2t divided by 4t squared. So basically we are cutting off at delta squared, where we get the largest contribution, epsilon squared times nu of epsilon. Oh, wait a second, I didn't do the density of states. Did I skip the density of states? Oh shoot, I skipped the density of states. So this was supposed to be the superconducting density of states, which I was supposed to do, but I'm out of time. Okay, we can continue this next time. I'll remind you where we were. I will first show you the density of states, and then we will continue. But remember this expression. We will use this next time. Okay. So that, this density of states, just before we conclude, I just want to point out that this nu of epsilon is also something you may encounter many times. If you divide this by n of 0, which is the density of states at the normal state, then here you have 1, and here you have delta, here you have minus delta. What you'll find is that this basically diverges, and if there is something that smears it, then, and when they do these STM experiments, they see these BCS-like structures. So that's a prediction of BCS theory, and we'll derive this nu of epsilon, and we'll derive the specific heat next time, and then we'll do the Gorkov derivation of the Ginzburg-Landau theory, and with that we'll end the course this year. Unfortunately, not so much, but at least we did some.